Okay, I'm going to invite you to get out of the periodic table and keep it out. And while you're doing that, I'm going to run down a list of things that at this point you can do really well. You can really easily look at any element on the periodic table and tell me how many electrons a neutral atom starts out with. It's not a problem. You can really easily look at anything on the periodic table and tell me how many valence electrons it's got. For main group, S and P. The D's we said are weird. You're all pretty good at that. You can tell me where those electrons reside. If those are S electrons or some S's and P's, you're good at that. You're good at writing representations of those electrons at this point. So we're going to add one more skill to your tool belt. And I forgot to print out the learning goal. But basically, you're now going to start to be able to represent any compound or any polyatomic ion, which we haven't talked about yet, we're going to, in this new way, in what's called a Lewis structure. We're going to start that off. There's a skill you have to build before you can start to do Lewis structures. And this will take you about 5 seconds to master. This is the electron dot notation. Okay? So, pick your favorite element. Main group, you. Mr. Galbert. Carbon. Oh, that's one of my favorites too. I love carbon. Being a carbon-based life form and all. So, to draw electron dot notation for any element, you start off by writing its symbol. Couldn't be a whole lot easier. Carbon. Once we've written the symbol for this thing, we look at how many valence electrons it's got. So, based on everything you know, carbon, which is group 14, P block, has how many valence electrons? 4. And we are only concerned with valence electrons for this. Only valence. Okay, now comes the fun. We start, okay, I'm going to give you the lowdown on this. Traditionally, we start at the top, we go around each side, drawing an electron until each side has one, then we start putting in the second electrons. Don't get too married to where these little dots are. So the electron dot notation for carbon, we start at the top, we draw an electron, that's an electron. We move around in traditionally counter or clockwise fashion, drawing more dots. Another dot, there's another electron. There's another electron. There's another electron. We're done, that's it. That's the electron dot notation for carbon. Now, let me ask you some probing, deep, insightful questions. Do carbon atoms look like little C's? If you had the technology to visualize a carbon atom, you would not see it stamped in the shape of a little C? No. No. It looks the same as every other atom. It's a nucleus with a bunch of fuzz around it. Are the electrons really looking like little dots? Are they really spaced out in these locations? No. So what I'm saying is, don't get married to, but there has to be one on each side! Because I'm going to teach you that, and then we're going to proceed to completely wreck it by moving those dots all over the place. So I just want you to understand, don't get too attached. We're going to build something. This is like, to use real-life experiences, this is like building a beautiful castle out of Legos with a toddler. You shouldn't get too attached, because the minute it's done, she's going to knock it over. Okay? So, Hannah Elliott, pick your favorite element, main group, something other than group 14. Something, if your favorite is in group 14, I apologize. Manganese. Is that main group? Nope. You could cover here and say, well, I meant magnesium. I just had a slip of the tongue.
I meant magnesium. I just had a slip of the tongue.
It happens to all of us. I understand completely. Okay, so we start off with the electron dot notation for magnesium. Doing what? Draw the symbol. So we got a big old Mg. Now, how many valence electrons does magnesium have? Hold up fingers. 2 is the loneliest number, blah, blah, blah. So, to draw the electron dot notation, here, we'll write down here, 2 valence electrons. To draw the electron dot notation for magnesium, you would traditionally, again, start at the top, go clockwise, and you're done. Remember that these are all representations of reality. This is not reality. I'm going to keep saying that because every year people get really freaked out when we start knocking this whole Lego castle down. Okay, let's practice a few more. We'll go to a new slide. Let's pick something out of group 1. Pick your favorite group 1 element, Stephanie. Potassium. Everybody loves some good potassium. Okay, how many valence electrons does it have? You're going to like this. We're done. That's it. That's the electron dot notation for potassium.
Sounds like a 200-point test on how to do that.
Oh, sadly, by the time you get to the metaphorically 200-point test, we'll have knocked this whole Lego palace down and we'll be building skyscrapers of Legos and, you know, bug spit or something. Okay, so we've got group 1. We did a group 2 element. We did our magnesium. We did a group 14 element. You guys have chosen nicely. Let's do a group 13 element. Tarek. I love aluminum. Aluminium, as the Brits say. And how many valence electrons does aluminium have? 3. Zoop, zoop, zoop. Now let me ask you this. In terms of your pattern recognition skills, if someone put a chunk of potassium to your head and threatened you and said, what do all group 1 elements have in common when it comes to electron dot notation? What's it going to be? They all have 1 valence electron, so they all have 1 stinking dot. So whether it's lithium or sodium or potassium or whatever else, down the entire group, it's going to look just like that. And for group 2, down the entire group, it's going to look just like that. And for group 3, down the entire, you get the picture. You know, just like valence electrons, because this is what we're representing, the electron dot notations for a group are going to look identical. So let's move up to group 15, shall we? Pick your favorite group 15 element, Mrs. Sullivan. Oops. Nitrogen, okay. Nitrogen, how many valence electrons? Hold up fingers. Okay, I see lots of 5s. So, 5 valence electrons. Well, it was all working out just smashingly up to carbon. We had 1 on each side. Wunderbar! So once we're up group 15 and above, we start off again, traditionally start at the top, traditionally go pretty much clockwise. And at the point where we've got 1 valence electron represented on each side of this atom, we then double them up. Okay? So that's the electron dot notation for nitrogen, traditionally. What would be the electron dot notation for sulfur? I'm working without a periodic table here. So, yes? Okay. Would it bear any resemblance to this? Oh, wait, no, I'm in the wrong. I'm thinking of phosphorus. Sorry, I'm 1 over. My apologies. Wait. Yeah, okay. Phosphorus. My apologies. Okay. So phosphorus would look like, guess what? The same darn thing. Minus stray marks. Oh, good. Somebody got one of the timers to work. So that whole group's going to look like that. So let's go to the next group. Oxygen. Everybody loves it. Nobody can live without it. None of us. Oxygen. How many valence electrons? 6. So 1, 2, 3, 4, 5, 6. Very, very messy. Okay, 6 valence electrons. Looks like a valence electron massacre happened. Okay, and again, for that whole group, it's going to look roughly the same. Now, can you legally represent oxygen like this? Yes. Because once again, do those dots represent reality? No. They're a representation of valence electrons. So, you know, like I said, we're going to build this Lego castle, and then we are going to knock the behoozes out of it. We're going to smash it to smithereens. And part of that is being okay with moving the little dots around. Okay, group 17, give me your favorite. McCarty, give me your favorite group 17 element. Bromine. Bromine, bromine. How many valence electrons? 7, just like all the rest of the halogens. Okay, so we start off, again, this is all, you know, what we do customarily or traditionally. Top, go clockwise. And there you go. Does it matter where that gap is? Does it matter which side only has one? No. Again, and you guys are being so good about this, so you have to promise me none of you will freak out when we start moving all the dots around, right? Okay. They don't represent real electron. It's a representation of the electrons. It's not reality. Okay. Okay, so this is good. This is easy. We've got one group in the main group to go, which is the noble gases, 18. So, pick your favorite noble gas, Katie. Krypton. I've always been a fan of krypton myself. Okay, 8 valence electrons. What's this going to look like? Two dots on every side. Now what's nice about this is this gives us a visual of perfection. This is what every atom, save one or two, would like to feel like. It would like to feel, hydrogen of course being the big exception. Everything wants to be surrounded by valence electrons, just like the noble gases. So this formation here is what makes everybody happy. Okay. Do you feel like you could pretty confidently draw electron dot notations for anything? Do you feel like you need practice on that? Okay. If you feel like you need practice, twitch. I'm watching for twitches. I'm not seeing any twitches. Okay. This is like the secret sign. Mickey Mouse flies at midnight and the ham is in the oven. You know. It's all spy talk here. Okay, so this is pretty easy, admittedly. Now, why do we do it? Good, we can draw dots. Why do we care? We care because this is the skill that leads you up to being able to represent compounds structurally. So, couple reasons that it's important to represent compounds structurally. If you're going on in chemistry and you're going to do things like physical chemistry or organic chemistry, it's imperative that you be able to represent compounds structurally to show how they're built so that you understand how they will react with one another and behave, and it allows you to do a whole bunch of things. It allows you to analyze the physics, the physics of the actual atoms themselves, which is just like beyond horrible. If you're not going on in chemistry, being able to represent compounds structurally, especially if you have any component of visual learner that is strong in you, is tremendously helpful as we move on down the line, because it gives you a second way to see reactions. And it gives you a second way to understand that these things are tangible objects. And so it really is helpful on multiple levels, whether you're going on in chemistry or not. So let's start with the real easy breezy stuff. Okay, so Lewis structures, they are sometimes called Lewis dot diagrams. That is sort of evidence of their relationship to electron dot diagrams, because we're using some of the same basic methodology. We're using little dots to represent electrons. And it's a visual formula. So the atomic symbol is what represents the nucleus of an atom. So when we wrote carbon, and we put our little valence electrons in, that C is standing in as a representation of the nucleus of carbon. Like I said, if you looked at a bunch of carbon atoms, they're not shaped like little C's. As cool as that would be, and as easy as it would make chemistry, it's not the case. It's a representation. And the dots represent valence electrons. Well, what we can do with these electron dot diagrams is we can move them into position so that we show how things share electrons. So you remember hydrogen? Oh, hydrogen. Our little friend who only has one valence electron and would be perfectly happy if it felt like it had two. Yeah. So here's something that very commonly happens. Carbon bonds to hydrogen. This is like one of the most common things that happens. We have lots of carbon-hydrogen bonds in the world. We talked about the fact that we're running our entire world economy basically on carbon and carbon-hydrogen bonds. Well, if we could take a hydrogen and move it over here, and then carbon would feel like it had 2 electrons there, and hydrogen would feel like it had 2. This might start to get them on the road, on the road to feeling more satisfied. Well, what we do is this. I'm going to have to move this around. What does that show? That shows the structure of a compound that contains 1 carbon and 4 hydrogens. It's methane, by the way. It's primary component of natural gas and cow farts and lots of other wonderful things. Fairly potent greenhouse gas, but good stuff to burn because it's got a low CO2 output per unit that you combust. So handy dandy stuff, very nice and very simple. Simplest organic compound there is. Now, looking at that picture, how many valence electrons does carbon feel like it's got? Remember, I said when they're sharing, it feels like it totally owns it. So if we look at our carbon, and I'll change colors to do this, well, carbon's got 2, 4, 6, 8. Is carbon a happy camper? Yes. And hydrogen shares to get to what? 2. So each of these hydrogens, this hydrogen feels like it's got 2, and this hydrogen feels like it's got 2, and this hydrogen feels like it's got 2, and this hydrogen feels like it's got 2. Are all the hydrogens satisfied? Yes. Does it feel strange to any of you? But we just counted those electrons twice. We counted them for carbon and for hydrogen. You're all okay with that? Okay, because that's one other place where people at some point go, but I counted that for... Right. They're sharing. It counts for both of them. So that is a simple Lewis structure. It's a very, very easy Lewis structure. You sense that there's a trap down the road and that these are going to get harder. They will. But this gets you the basic idea. It is just a way to represent compounds in physical space. Just like the different representations that we've had of the atom itself, is this right or wrong? No. Are there other ways to represent it? Yes. And they each kind of allow us to think about different things. So this is one. Let's practice a few simple ones together, and then we'll start into the rules. And the other, here, let's do one right on this page. I'll move this over. Let's do ammonia. Okay, so ammonia, you may have used household cleaning ammonia. Ammonia is nothing more than a nitrogen and 3 hydrogens. And I'm using a lot of hydrogen compounds here because they make some particular things easy. Okay, so what was the electron dot diagram for nitrogen? What did that look like? 5 valence electrons. And very often it's shown with 3 on the top, or 2 on the top, and then 1 on each side. So, if we stick 3 hydrogens in the places where it would be most obvious to stick them, you know, you kind of look at that and intuitively go, oh, there's a place where it could share there. Oh, there's a place where it could share there. Oh, hey, it could share over there. And you kind of intuitively stick things where they go. Now, the thing I didn't tell you yet about both the methane picture that we drew here and about this nitrogen picture is there's one more step that we usually take with a Lewis diagram, and I'm getting rid of my little black circles. Once we're at a point where we have 2 electrons and they're being shared and we don't really need to do anything else with them, we typically go ahead and replace those 2 dots with a single line. So it looks like this. With a single, it's a single line, it's a single dash. And so each single line like that represents 2 electrons. So when we count up electrons, that line, yes sir?
But you can't do the top one.
You can't because they're not shared. And that was the next point. So, you know, the final, okay, we'll pick this up on Monday. Have a good weekend.